just share my presentation first.
Good
Or
afternoon. Good afternoon, everyone. I, Ambika Dubey, welcome you all at the live webinar series organized by IEEE Student Branch, Acropolis Institute of Technology and Research. Thank you for joining us. Today, we have a very special guest, and we are very grateful to have with us Dr. Chandrabhan Singh Kushwa. Dr. Chandrabhan is a postdoctoral researcher associate at University of Bath, United Kingdom. He served as a technical officer at ngenics Limited, UK. His research activities include designing sensors, integration and miniaturization of adaptive cardiorespiratory system, implantable wireless pacemaker system. He earned his Ph.D. from IIT Indore and his master's from SGSITS Indore. He has 11 years of experience in industry and academic institution. He has authored and co-authored more than 30 peer-reviewed publications and two patents. Now, sir, I would like to request you to lead on the presentation. Now onwards. Thank you.
Thank you, Ambika, for this nice introducing me on for this public. And I also would like to thank Professor Lalit Bandil, who gave me this opportunity to collect and share this knowledge from my past experiences and recent, I would say, search about the VLSI. And I'm also privileged to discuss this very important and interesting field of electronics with you all people. And so thanks and good afternoon to all of you to being here. So I would like to start with my presentation here. And I would say that it is this information which I gathered and the knowledge which I have, it is very, very important and very interesting. So it is going to be very essential. And I think every VLSI enthusiast and everyone will get benefited from this discussion. So anyway, let me tell you that I think this all VLSI and electronics has started from the World War II. Normally, wars are not good in any sense, but somehow we got some kind of a new technology came from that World War. And it started actually from the radar system because people wanted, or one country wanted to detect another country's weapon and ships and their aeroplanes so that they can just destroy them as soon as possible. So it started from that radar system, which needed to have one silicon crystal material. So all the different institutions around the world, including Purdue, Bell Labs, MIT as well, University of Chicago was also there. They joined forces and built better semiconductor crystals for that radar system. And eventually, within a decade, this superb understanding of crystal growing would pay off. And at Bell Labs, they grown first germanium, I would say the semiconductors that was the heart of first transistor, I would say. So from then, I think from my perspective, semiconductor electronics is rated as a major field of endeavor. Keeping the history in mind, let continue with the outline of my presentation, which is yeah. Please, somebody can you hear me?
Yes, sir.
Okay. I thought somebody would like to ask something, so that's why I just prompted. So this presentation is all about the VLSI, and specifically, it is based on a recent trend, what is currently going on in the market, especially in the consumer market as well as in the research and industry. Let's go through my outline, which we discussed first about the what is VLSI. Actually, I would like to introduce the VLSI, although it is already started in the, I would say, in the class 9 of CBSE course. Unfortunately, I was pretty old in that sense because in my school I was not introduced to VLSI or any kind of semiconductor, I would say, systems. So it would be easy for the people that those can understand what actually VLSI is. So first we will be discussing about the VLSI briefly, and then we will go to the history of how the first transistor, and when, I would say not how, I would say that when it was came into the picture, and first IC also, integrated circuit, and the computer. Actually, that would be a programmable computer, not the mechanical or electromechanical or analog computer. It is a programmable, first programmable computer. We will just see when it was introduced, and then we will see the Moore's law, which is very important because all the trends which we are going to follow or discuss, it is based on that Moore's law. Actually, it is a prediction. This later on it became a law. And then in the last, we will discuss about the, I would say that the application of the VLSI, which is all around everywhere, wherever we can think about, and its opportunities for students, for teachers who are working on them. They can get some kind of insight what is going on in the industry, and what we can, I would say, do in the research and also in the industrial setup. So let's move on the introduction of this presentation, which is about the VLSI. Actually, VLSI, as I think we all know, that it is a very large scale integration. And why it is called a very large scale? Because we are integrating millions of billions of transistors. Especially in current scenario, we have a small chip, around 100 millimeter square chip, that can contain 2 to 3 billions of transistors. MOSFET, specifically MOSFET transistor, and new current technology as well, like FinFET and gate all around MOSFETs. So that is why we are integrating a large number of transistors, especially. That is why it is very large scale integration of those transistors in a single silicon chip. And we can, because this field is very vast, so we can especially we can separate this field into two field of research, which can be divided as VLSI design, where we design the circuits based on the transistor models. And when we finish designing those circuits and connect those circuits together to make a system, then we will go to the fabrication. Well, what does it mean? We are going to build an actual hardware that will reflect whatever we needed to do with those circuits. And that can be done with the help of VLSI technology, where we will follow the specific process, especially lithography, to design and develop or fabricate that system, that computer system or microprocessor or any kind of electronic device that is very, very complex. Although it is very complex, we can exploit that complexity in terms of our applications, our processing. So that is why that complexity also give us a chance to make very, I would say that, efficient system. So that we will discuss. Although these things, I was fascinated that in class 9 of CBSE course, they introduced VLSI, and also in 12th standard of the CBSE, they have introduced many things like semiconductor electronics, materials and devices and circuits. I was so fascinated that if I could be there, then it would be easy for me to understand VLSI, and from then I could go into another way of researching and industry. Anyway, we can think about. So we will start with the transistor and ICs, and then we will talk about little bit. Uh, I would say the computer and memories, any other things. So let's start with the first transistor, history of first transistor. So like I will also just go through this one because as we already know that the first transistor was, I would say, started from the World War II, and this was around 1940. Before World War II, we started from there, and then first integrated circuit came around after 1 decade, or I would say that that was the first integrated circuit in around 1950s, and then microprocessor came, the MOSFET or and I would say the field effect transistor MOSFET. They came after 2 decades because of the difficulty in the technology which can fabricate the MOSFET devices, and that gave us a speed and power also. So that is why it came around 1970s, and then it still continues. So from the 20th century, starting of 20th century, it is still continuing. And based on those predictions, how our devices are going to downscale, how our performance of the system is increasing, the Moore's Gordon Moore has predicted that trend and made an assumption that it will double, means the number of transistors in a single chip would be doubling in I would say 1.5 or 2 years period time. So that was his prediction, and later on, when this trend was I would say successful, it was become a law. So it started in the early starting of the 20th century, and it is still continuing. So that was very interesting thing to know about that. So this is just a brief, I would say, list when transistor was, I would say, introduced, and the idea of the transistor was introduced, and it was something around 1906. Why Lee De Forest? He was using the, I would say, the vacuum tubes, and they were just like triode, because normally we have to control the flow of the current, so we need another terminal, or from one terminal to second terminal we can control the current, and we needed one another terminal, that is a third terminal. So that was, it is called triode. So two terminal diode and three terminal, it was triode kind of device. So it was the idea of the transistor, which was later on, I would say, successfully found by Julius Edger in 1925, and he made a MOSFET, or MOSFET kind of device. Not actually MOSFET, but it was a MOS idea. So it was field effect transistor. So that was from Julius Edger. And later on the similar time, 1948 and 1947, people in the Germany, those were Hubbard and Heinrich, they were working on the three-point contact transistor. Similarly, on the US, the people were at Bell Labs, they were working on the this similar kind of transistor, that was a bipolar junction transistor. And for what happened there, that the John Bardeen, they have applied for the patent, and they patented and protected their idea of the transistor, and they got it. But unfortunately, the German people, they could not get that one. So for that groundbreaking research or invention, those group of John Bardeen, Walter Batten, and William Shockley got Nobel Prize in 1956. So that was the actual transistor, I would say, that changed the world forever. And later on, after, I would say, for after a decade, the people at Bell Labs, again, they were able to fabricate the MOSFET in 1959, and they were able to design other circuits as well. So on the basis of these transistor development at Bell Labs, James S. Kilby was able to design some kind of, I would say, that two transistor IC. That was the first IC that was developed by J.X.S. Kilby, and that was just a two transistor. But the idea was that those two transistors can be fabricated or made at a same chip or same substrate or same area. So that is why it was the first, I would say, idea of the integrated circuit or IC. So that is where we got the idea and also development of the transistor. And on the basis of those transistors, we are still building a different kind of ICs and processing system. But the idea of the first computer, was not the basis of the MOSFET. It was based on the vacuum tubes, which we discussed. That was around 1906. They was developed. So the first programmable computer was it was called ENIAC, and it could be programmed accordingly. What kind of series of sequence you can process. And whenever you are processing, it was difficult that those vacuum tubes used to just burn out. So that was difficulty. But this was the first programmable electronic computer that was introduced in around 1946. So, and later on, because of the development in the semiconductor, many different kind of processing units, I would say, calculating devices and system, they have been developed. But in after, I would say that the 2 decades or something, as we discuss about the ICs, so Intel has developed one first microprocessor that was based on the MOS device, and that was around 1971. So it was an Intel microprocessor that could be utilized as an actual semiconductor MOS technology based microprocessor. So that was really, I would say, great opportunity and achievement also, because we were able to design a semiconductor microprocessor. And surprisingly, what was the feature size that was? It was 10 micrometer. Normally, feature size means the length of gate of the MOSFET. It is the basic definition of the what is the feature size, or what is the technology node, or what is the process node. So it is the 10 micrometer at the time of 1971 when it was introduced, and it was containing around 2250 transistors, and that was the density at that time. But if we compare from today's density, it is around it would say 2 billion transistors. So it is so complex and so dense at this moment of time, and a similar space we can think about. So this was the first microprocessor that was introduced by uh, Intel, and at this current time, even day before yesterday, they announced that they would be going for the volume production for gate all around and FinFET devices for next 5 years, and that would be a technology node of around 5 nanometer to 3 nanometer technology process node. So we can understand what how technology has tremendously changed during this time. So let's say, we will discuss about, because we have seen the transistor and how it started, how ICs has been introduced, and how microprocessor came, and from that time, that Moore's law was continue motivating us to design more sophisticated, more denser system, more powerful, and high speed system as well. So this was the first prediction of the Moore's law, that he was just predicting that, or observing from their past experience, or I would say industrial production experience, that how the transistor will going to downscale, and how this trend will continue for 1 decade at least. And he just predicted for 1 to 2 decades, not more than that. And later on, he just revamp that one to next generation, and still he is alive, and he is working. I don't know exactly where he's working, but he's still alive, and its law is also still alive, although we have to modify in the other sense that it was not actually working, but somehow we have to find out some kind of new devices. Those are 3D devices as compared to the planar 2D devices. So because of introduction or the research in that field, we are able to continue with the Moore's law at this time also. So this was, as I previously mentioned, he predicted that the number of transistor in an IC will be doubling in a 2 years period. So that was his basic assumption, and I would say that just a projection or prediction. So that was the beauty of that prediction, that it continued today itself. And because of that, if we see here, it would be, I think it would be difficult to see because of it is so complex. It is very large scale integration, so it would be very complex and dense, and it would be difficult to see, because we are talking about the nanometer range, although it is not in the nanometer range. So because we cannot see the transistor in that range. So because of that scaling in the transistor, it was giving us the opportunity to speed up our processing, because of we have reduced the capacitance that was offering through the transistor or big transistors, and because of that we could achieve the more power in the system or computing system, and we could achieve the parallel processing. Because if you see in the current scenario, or even for last 22 decades, or even before that also, we were thinking how can we improve the speed, and we were able to understand if we process the sequences or the programs parallel, then we can achieve that one. And based on that idea, we have developed the core system. So if you see, I bought my laptop in I would say 2006, and it was having core solo processor. That means it's just one core, but it was saying, Intel was saying, it is a one core system, and later on dual core, quad core, and nowadays it could be achieved around 28 cores. We will see that one. So because of that downscaling, now we can see it started from around 1,000 transistor, and we saw that Intel first uh, microprocessor was having around 2,250 transistors in there, and it was 10 micrometer technology. And now so that was a large scale integration. It was not a very large scale integration. If we say the scale or the amount of the transistor where VLSI started, it was around 10,000 transistor, and it continued there. Even we tried to change that name of VLSI to ULSI, and later on also, but because of that, there was no limit how down we can go. That's why that VLSI is still stuck. That the technology which is started from 10,000 transistor, it will be VLSI, and it is continuing now onwards also. So that's why we are calling it VLSI. Still, even there is another terms you can find, that is ULSI also, ultra large scale integration. So from that time we are here somewhere. 2018 there was development also going on, and that was having some, again I'm talking about the millions to billions transistors. So it would be millions of standard cells. We will see what is a standard cell. Also millions of memory cells in a single memory, I would say, chunk. So these are based on this prediction. So at this moment we are having billions of transistors in a small area of 100 square or millimeter square. And if we see here, this is the I would say the timeline from where we started. It was in 1971. It was 10 micrometer feature size. As I talked about, feature size means the gate length of a transistor, especially MOS transistor. And now we have already developed a 7 nanometer transistor and the processing units based on those transistors in 2018. And we are moving ahead for the 5 nanometer, 3 nanometer devices. Although we are having many different challenges and difficulties to build these kind of systems, because as I told that these fabrication technology, it is difficult to fabricate new device because new device need a new setup. For example, if you design a new bottle, then you have to make a different process so that you can uh, realize that pattern. So you have to change your whole factory setup from designing to fabrication or final product. That is a similar fashion. If we see there here that if I'm going to change the transistor, I would say dimension, if I change the transistor design, then it will also affect our fabrication process. That's why it is very, very difficult. So because of that difficulty, only few, even I would say just three uh, fabrication houses, or it is called foundries, they are able to develop these feature sizes nowadays. We will see what's that. So here this I just created this slide based on the applications which we started from 1947, and there was a different application like transistor radio, mini computer. They encourages us to develop more power and reducing the size of that processing unit that was earlier started from that, I would say, programmable computer that was in-house in a single, I would say, the room. And nowadays, or in 1971, it started to reduce that size to on a desk, and that continued. So on the basis of our need, like if we talk about the internet, then we are working for 24 hours or more than that. So we need a small devices like cell phones and laptops or iPads. So based on those application on, and also based on those trends which we could see through the Moore's law or prediction of other scientists, so that we could achieve these kind of applications, and we could be able to design those kind of sophisticated and denser system, also the fast system. So it continuing till now, and based on different application, now we are going to the era of 5G, which needs a very high speed data transfer as well as the data processing. And because of that, we need to have some kind of system those can allow us to process that data. And if we see what kind of data we are having in these days, so if this blue is just a cloud where you are throwing different variety of data and constant data, and you have to process that data, I would say, in the real time. You have to store that one, you have to process that, you have to send that and transfer from one side to another side. So it is very chaotic environment where you have to deal with this kind of processing systems. So because of that kind of application, you need to move forward. You need to find some different kind of systems, and for to build those systems, you need to find out different kind of devices if there is a problem with the current or existing device, and which already happened. So because of these kind of application, we have to find out new devices, and that is why we moved from BJT to MOSFET. And we also had previously like combination of BiCMOS and different kind of devices. Those was combination of previous and new technology. and that moved from one technology to another because of the problems and challenges we were facing to cope up with the application, which we discussed in the previous slides and also in this slide. So based on those challenges, we have moved forward with the device design, system design, and also the fabrication units. And if we talk about the device design, so we can start from 10 micrometer, but we cannot because it is a pretty long history. Yeah, please.
So your slide is not visible actually.
Uh, just a second, I will share again.
Sure, sir.
Is this visible now?
No, sir.
Still, you are not able to see it?
No, sir.
Okay, so I will just again share the screen. So wherever you have the problem, just let me know because
Yes, sir.
yeah, thanks for letting me know. So this is, I'm going to share my screen again.
It's visible now, sir.
Okay, so that's good. Okay,
Yes, sir.
so I will just, even I'm not able to, yeah, it is slow in my system as well. So okay, so we were here. So
Yes.
we can take the, I would say, the first transistor to this point, but as we are discussing about the very large scale integration, the current trend. So I can start from a MOSFET, which was around 90 nanometer node, and 90 nanometer node means it was a gate length of 90 nanometer. But if you can ask me that why gate length is 50 nanometer here, so it is because if you see it trends goes to another technology nodes, and this is because in 90 nanometer technology, single, for example, if I can improve or enhance that technology in the same technological node, then it would be good for me. I don't need to go for another technology node. So that is why the different design houses and also fabrication unit, they were able to enhance that 90 nanometer technology node to achieve the gate length of 50 nanometer. And same happened to another technology. And this is the MOSFET SAM image. It is called scanning microscopic image. So that image gives us that this is the fabricated device where this is a source and this is the drain and this is a gate and is covered with the silicon dioxide, and that's and also the metal, which we can apply the voltage, and that field will affect the channel here between source and drain, and that in that sense you can control the flow of current, and then you can control the speed also. And that was the basic operation of the MOSFET, and it continued till the point of 32 nanometer device. So after 32 nanometer, when we are going to reduce that size here, so it was difficult because the electric field was so high that it was creating a leakage from body to gate. It was called gate leakage current. And also, like there were different challenges. I think somebody would be knowing the short channel effects. So because of those effects, you were not able to control the gate current. And if you're not able to control the gate current, then how can you switch on and switch off your transistor? As I talked about the gate leakage current, your transistor is still on, even then you have switched off. So that was the main problem, that you was not able to control the gate. And that is where the FinFET device, so new device, where if I would be able to control the gate more efficiently, is that possible? Yes, we could achieve that one with the help of 3D device FinFET. We will see what is that FinFET. Otherwise, at this moment there is a fin which is vertical. That is why it is called a 3D device. It was a planar device because you can deposit different layer on top of one another, and you can achieve and you can make a planar devices that sense in the vertical direction. But here you can directly erase that silicon, I would say fin, and that was kind of silicon trench isolation that can just, I would rise from the bottom of the wafer, and you can place a gate, a metal here, and from three sides of it you can control your current. So that is why we were able to control the gate, and we were able to control the current. We were able to increase the speed because of that current density has been increased, and we were able to process those programs more efficiently without worrying about the scaling the transistor. That is where we have come up from different point contact transistor to bipolar junction transistor and MOSFET transistor and FinFET transistors. So as I was talking about these technological nodes and what is there, and also that how long or how much we can scale down the transistor. If we think about the tunneling distance between is around 3 nanometer of the silicon material, then if we think about the what is the distance between atoms of that silicon, it is around 0.3 nanometer. So is that possible that we can go ahead with that? At this point, nobody knows, but let's see what happens whenever we are going to downscale these transistors further. And before that, we just quickly take a look on what was the technology node. So this was previously predicted that the half pitch between two metals. So these two metals comes into the picture when you are going to design a layout of a circuit. So based on these two metals space, we could say that the technology node means the half pitch. But at this point of time, it is not actually valid in case of 3D devices, because we have different model for the gate length. That is why, or effective gate length. That is why it is not valid. But still, we are talking about the technology means gate length. Theoretically, I would say. And also, different technology node has been, I would say, are different for different design houses. Like for example, Intel is designing 7 nanometer, and same technology node is used by IBM. They would be having different technology nodes internally, because at the same technology node you were not able to exactly predict, exactly design the same design for two design houses. So that is why there are different scenarios, but for common concept, if we talk about, then technology node means gate length, for especially for the planar devices. So we can also see how these two devices are different. So these are the same image of MOSFET, where this is the drain, this is the source, and this is the gate. So it is a planar device where we were talking about, and this is the FinFET, which is this. If I just see that cross section, which we have seen in the previous slide, then you will see this is the fin. It is vertically going up from the wafer, and there's a source. This is drain, and this is the gate. And gate can, I would say, cover this channel area from this side, top side, and the back side also. So from three sides, it can cover the gate, and that is why you can control the current flowing through source or drain, and that's why you have the more gate control. And that is the basic difference between why we are going from MOSFET to FinFET, because we can control the gate more efficiently, and we can reduce or downscale that transistor of FinFET further down to the sub-nanometer regime. And because of that kind of fabrication challenges or difficulties, you can see from the start of that 180 nanometer technology, many foundries or fabrication houses were there. Those were able to produce these kind of system on 180 nanometer technology. As technology, I would say, enhanced or further improved in terms of scaling of the transistor. Scaling means downscaling of the transistor. Then it was difficult to manage that one. As I told, and I gave you analogy, that if you are going to change your device, then you have to change your whole processing setup. So that is why it was so difficult that while we are going to downscale at the level of 7 nanometer to 5 nanometer, only few foundries are working on that. And recently they have developed FinFET devices. Even they are commercially available, and the system which are based on i7 and i9, they have the FinFET devices inside the motherboard. So we can see how difficult it is, the fabrication. So as we are talking about the transistor, we are talking about the system, we are talking about the how those systems are made in hardware. So this, from there we can see the what different kind of challenges we have got, what kind of different new ideas in terms of the devices, or especially the MOSFET devices we have achieved, and we are going further for that. So we will see that what devices these FinFET devices has also challenged, and how these are going to be fulfilled in the next decade or more. So this is the projection from International Roadmap for Devices and Systems. Previously, it was IITS, that was International Roadmap for Technology and Systems. So that was overcome by this IRDS. So they are. This is just projection. So this is just like we are thinking, we are deciding exactly what would happen if I'm going from 5 nanometer to 1 nanometer or less than that. And this technology node is just not I would say scaling the gate length. It is also depends on what is the field you are generating or you are affecting your transistor, and not only these 2 or 3 parameters. There are many parameters like capacitance, gate capacitance, and source drain capacitance. Many mobilities, many I would say the device level parameters as well as material level parameters, and some parameter those comes from the experience of foundries as well as from the layout uh, section. So based on those, we decide what is the technology node. So at this technology node, for example, at 5 nanometer, we have the power supply of 0.7 volt. It is so low. And because of that, we also have some challenges of the headroom between 0.7 volt supply and the threshold voltage of this device. So we have those challenges, but we will not be discussing this one, because we are talking about that how this technology is going to change when we are going to scale down the transistor from 5 nanometer to 0.7 nanometer. So what is happening here, that we are I would say that stacking the device. So if you see here, we are stacked 2 devices together on top of other, and on the another picture we can see that this is more stacking of the devices from one device to another device. So we are going in vertical direction, because of we need to have more control over the gate, and so that we can improve the density of that current, and because of that density we can achieve the high performance computing as well. So that is why if we are going to downscale our transfer from 5 nanometer to further, we have to achieve in it is a just one way. It not just this is the way, but it is a just one way depending upon what technology we already have. So we already have the FinFET transistor. Now we are achieving another transistor, similar transistor, but with the different device structure. And if you see closely, this device is just having three I would say this device's gate is controlling the I would say the gate, or this gate terminal is controlling this channel from 3 sides. But here, if you see closely, this device has a control over the gate from all the sides. So new technology is coming with the gate all around transistor. So gate all around means your gate is all around your channel. So you can control the channel more efficiently, and you can also reduce down at least for some decade for 1 nanometer or less. So this is the benefit which we just talked about, that what kind of I would say that the ideas those inspired us to reduce that size of the transistor. So from 2011 to 2034, we would be going in that direction, unless we have some other kind of devices or other kind of structure, and we are already working on those transistors. But I'm discussing here these transistors only because these are using by the industry at the current scenario. So that's why we are discussing the current trend of this VLSI design field. So because of these advantages of increasing the number of fins, we can increase the I would say efficiency of the system, and reduce the capacitance as well. But normally in the FinFET devices, for the analog devices, analog people, it is difficult because the capacitance is rising of these two, for example, vertical direction, and also self-heating is there because heat will just go from bottom to top, and that's also the difficult challenge for the analog device engineer, and that will introduce the flicker noise and on top of the thermal noise. So these are many different things to discuss about, but other than that, we can have more control over the channel, and we can achieve that one with the help of stacking of these devices. And we can also see just one idea that how these devices are going from FinFET to gate-all-around MOSFET, and these are called nanosheets. These are the scanning electron microscopic image from IMEC and IBM. It is recently published, and so we can see these. This base is silicon, and you can increase that one, trench isolate, uh, and you can raise that one up to a particular height, and from there you can deposit layers of silicon dioxide, and then again you can deposit, you can diffuse, you can pattern. So as we can see, it is so difficult that how can you make a this kind of structure or circular structure, and you can wrap that channel through the gate. So it is so difficult in fabrication, especially patterning and etching, because you have to deposit one layer, then you have to etch, then you deposit a layer, then you can again etch. So, but we are discussing about the device structure. So these are the gate-all-around nano wires and nano sheets, and because of that, we could achieve the new dimension or scale dimensions of this transistor, and we can go further. And how does it look like in a wafer? We will see that one. It is just a wafer, and that was presented by Intel, and that was a KB Lake wafer. So KB Lake means it is a microprocessor generation. For example, you have the Intel i7, i3 microprocessor. It has some kind of generation which is a microprocessor. So i9, i7 is a whole system, but what is the architecture of that system is KB Lake kind of architecture. It is not for i7, i9. I'm just giving an example that this KB Lake is a micro processor architecture. So these blocks, so this is a full wafer, and if you see here, these are some rectangular blocks here or square box here, and these single block is representing one single microprocessor core and each microprocessor has around 10 cores. So how tiny it is, and each microprocessor has at least 2 to 3 billion transistors. So let's see more. I would say, and this full wafer would be having around 400 to 500 microprocessor. So this is these are the numbers. But just take a closer look on this. So this was the small piece from that wafer, and later on after processing we can cut it from there, and we can package that one in a specific manner that can be utilized for our microprocessing unit. And take a more closer look there. So this is that tiny piece of that fabricated wafer, and that has many different kind of I would say the blocks, building blocks. Like it has 8 cores, CPU cores, and there's a system agent, means it is a I would say that it can allow you to connect with the CPU cores efficiently and with the high speed clock rate. And similarly, like here, these are the interconnected agent, ring interconnect agent. These allows the data transfer between two cores efficiently. Similarly, here GPU and media. GPU means graphical processing units, so they need a high speed communication and interconnect between the peripheral devices. Also, there is a DDR, double data rate periphery, which allows you to interconnect with the CPU and devices. So this is the complex system. You can understand how complex it is. It has around 3.052 billions of transistors, and it runs on a basic frequency of 3.6 gigahertz here. And so this is the microprocessor which you can think about, and it is running on your system. And this came from the previous history where we started from just 2 transistors in a single piece of semiconductor material. And now you can have the billions of transistors in a single small piece of device. And the size of this processor would be around 100 millimeters square or less than that. And especially, I would like to say that this has been built on 40 nanometer technology. And if we see here, it says 40 nanometer plus process. So as I talked about that, if at 90 nanometer technology, I could achieve 40 nanometer feature size. Similarly, if I can enhance my fabrication process, if I can enhance my design process, then on the same technology, I can improve that technology node or processing. That is why it is called 40 nanometer plus plus, because it is enhanced process there. So from this picture, we can understand that i9 processor or the current scenario can have billions of transistors. Those are working on that. And with that slide also, with this slide also, we can see that how these number of cores are increasing from the time of, as I'm talking about 2006, but it was not in 2006, it was earlier there also. So the idea is now going to increase the number of cores in the system. And currently you can buy these number of cores systems from Intel and also other I would say AMD and ARM, they are also building, but especially for the consumer market, these are the server details. But similarly, you can find 28 cores microprocessor for your domestic or your desktop as well. So this is the availability of a current processor, and the current trend is going on like that. And these CPU cores are built up on the basic modules or basic cells. These are called standard cells. And those standard cells are also going to change, because of, as I told about that, if I'm going to change the device structure, then whole system will change till the fabrication process. So this is the FinFET standard cell that was developed around 2015, and it is continuing to downscale. Because of that, we were discuss about the stacking of those FinFET devices on top of each other. So that is allowing us to change the small standard cell size from 2015 to 2020 or further downscaling. And these standard cell are now built upon the technology of gate all around devices that we discussed about that one. So because of that, we can achieve that, I would say, smaller feature size, a smaller transistor, smaller microprocessor, and also speed. We are going to enhance speed. There are many challenges. These are just benefits, but there are many challenges, as we discussed about. For the MOSFET, there were short channel effects, there was a leakage effect. Then in FinFET, we are talking about how can you create a perfect fin that can allow you to gain more control over your channel. So these are the challenges, and these are some fabrication, also design issues. But as we are discussing about that, these standard cells are the main building blocks of the microprocessor or any processing unit. And if we see the projection or the trend, how it is going about these standard cells, also the memory bit cell, as I mentioned previously. So we see that they are increasing in that fashion, that from 2020 it will go to 142 million gate in just a millimeter square area of that one, that is 140. So this is the density, and in the similar fashion, we see that the SRAM bit cell can also be achieving that kind of density in 2034. It is coming from 2020. So around 300 million bits per millimeter square, we would be achieving that. And as we know that if you need a fast processing, then you must have the SRAM, big XRAM, or I would say that the fast SRAM cache memory. Because if you have cache memory and near to your microprocessor, then you can easily and efficiently, or with the high speed, you can process the data. So that is why in the current scenario also we are having in-memory application, where your microprocessor itself has a huge amount of memory. So that's why it does not need to communicate with the external memory or external L3, L4 cache. But it is very difficult, because SRAM itself consume a lot of power, especially from the microprocessor, and they are the main building blocks. Those are consuming more power. That is why it is very challenging. But we are talking about how trend is going on from 2020 or before that to the point of 2034 or in coming decades. And what about the number of cores? If we see here, the number of cores will also grow up. For example, here GPU cores, we discuss about GPU is a general graphical processing unit, which normally we use for the graphical applications, just like gaming or also designing, CAD tools. Many things are there, and also CPU cores. So they are also going to increase in the sense of that our system or our microprocessor will be going to denser and denser in that sense, and we are going to achieve that one to process that high amount of data we discussed about with the help of multiple cores in a single system. So this is the trend which we are going to achieve within few decades, and we are also have achieved earlier with earlier technologies. And this is the trend which we can follow further down the scale. And with the some challenges of device structure, with the bit cell design, with the standard cell design. So on the basis of those building blocks, we can also think about that what would be the memory structure or memory technologies for the current and also the futuristic microprocessing units. Then we can think about that there are many different variety of memory available. Especially we can separate memory with two different kind of I would say functionality, that is volatile memory and non-volatile memory. We know that the volatile means whenever you are switching off your power, then the data whichever you have stored in the memory, it would be vanished. And on the other hand, if you are talking about the non-volatile, that means then whenever you are switching off your system, it will be still there for a long time. Even with memory card, you can attain that one for some years. And for hard disk, it can last for decade. Even in my hard disk, I'm using for I think last 12 to 13 years. So that's the basic difference. On the basis of that difference, we have the SRAM that is especially needed for the microprocessor, especially for L3 or L4 cache memory, and DRAM, which we have in our system. Those are the dynamic random access memory, and this is a static random access memory. And this memory contains the standard SRAM cell, as we talked about, and that based on the transistor. So that is why it is volatile memory. And DRAM is also volatile, but you have to recharge those capacitors which are based on which are basic transistor I would say component inside the DRAM. So in that fashion, we have a microprocessor which should have these two kind of memories. Also, as I was talking about the non-volatile memory, and the non-volatile memory has new kind of memories, which is we will discuss, and we will just think we briefly go through that. Otherwise, these memory has different kind of structures. So like SRAM and DRAM, they are, as I told about, this is based on the silicon transistor, but they are not based on the just silicon. They are magnetic memory, they are ferroelectric memory, they are resistive memory. So that's why they are different in the sense of the structure as well as the material. So that's why we have to think about device structure as well as the material. We will think about and talk about that also. But before that, how these memories has changed. So this static access memory was developed from the BGT to MOSFET to FinFET, and it will go continue to the gate-all-around MOSFET as well. I can take an example. For example, this memory bit cell is a FinFET 40 nanometer memory layout. It is not a schematic design, it is a layout. So actual hardware layout that would be fabricated by the lithography or process of that FinFET technology. And this was patented also because I was able to design this memory, and to save that area, I just stacked up two bit cells. So this is the 2-bit cell structure. So 1 bit cell is here, 1 bit cell is here. If you can see here, I just placed, or I connected this to bit cell in a manner that it will save your full area. So you can just multiple bit cell in a single SRAM core. So in that sense, you can see here how complex it is. So these vertical lines are fins, and these horizontal lines are active area and a connection there. So in that sense, you have to achieve these fins, and you can increase the number of fins to make different circuits also. So this is a FinFET device which has these are the fins, and these are the transistors. So these are many transistors here. There is 8 transistors. These are pull down transistor. So these are 8 transistor SRAM bit cell made in 40 nanometer FinFET technology. So this was an example of bit cell. How would it look like into the future also? So similar bit cell can be designed with the help of gate-all-around gate also, which is going on. And how different kind of memories has been researched in the past. So this red is data which is available actually. It doesn't mean that other memories cannot achieve that kind of processing, or I would say the application, because of the resources like the I would say the lab facilities and also the fund. So because of that, we were not able to get the data for these. Otherwise, if you see here, these are the memories which are promising for the future and also current processing unit. And out of these all memories, we can select few memories which are promising, and in the current scenario, they are developing. So these are the spin talk memory, phase change memory, resistive RAM memory, and conductive bridge random access memory, and also ferroelectric random access memory. So you can see that how they are very, very different from each other, and also how they are different from previous FinFET or MOSFET static random access memory, or uh, um, I would say that the floating gate kind of memory. Floating gate means there is a gate where it is floating between your body and your gate, and where you can trap the charge, and that charge in the terms of you can utilize as a I would say data. Whenever there is a charge, it is one. Where there is no charge, there is zero. So how they are different from these kind of memories. So this is the trend which is going on, and it's still we are searching, and we are studying these different kind of variety, because it is difficult to cope up with that memory, because SRAM consume a lot of power in the microprocessor. So to show these designs of memory, that we can understand how it is difficult to achieve that nanoscale region. So for these memories, processors, and transistors, as I discussed about the device structure, microprocessor units, but we have to think about the material as well, because silicon is in abundance. That's why we are using, and it has very good property. It is semiconductor, so that's why we are using that one. But we have to think about new material, because silicon itself has many. As I told about the point 0.3 is the point 0.3 nanometer is the atom difference or atom distance. So that's why we are also trying to find out new materials and researching on those new materials. And these can be many different materials like graphene and carbon nanotubes. We have already working for a decade, and it is in production also, but it is not a commercial one. So we are researching all these different kind of memories, materials, especially. And as we saw that the nanowire, those are nano sheets which were developed, silicon and germanium nanowires, because at this point of time we also struggle with the silicon. So what we are doing in the even Intel is working on the silicon as well as germanium mixed uh, devices. Those can be applicable for high speed processing. So like this, so if there are different kind of, these are the only few materials. You can have different combination of materials. So for the microprocessing units or the transistor. So like that, we have to think about device as well as material perspective. And for with the material perspective, we will also understand and how it will affect us, affect our fabrication process or technology of the new device. For example, FinFET or incoming gate all around, or incoming different material combination of that material and the devices, because ultimately we have to fabricate these devices. So for that also, you need to have different technology to fabricate these miniaturized devices. So here we already have some kind of lithographical technology, where at this moment we are using extreme ultraviolet technology, which allows you to features that tiny device. As I given you the example of bit cell, if you remember that there was a two fins separated wires, wire, I would say that the pitch size of 20 nanometer. Then how can you achieve that 20 nanometer within the 193 nanometer wavelength? So we are using dual patterning for that. So that is an example that how can you achieve that kind of feature size with this current technology. You have to find out new ways, because we are also lagging with that patterning. As I told, that patterning and etching would be a difficult task for the new technology. So now we will just take an overview on what kind of application we had previously, what kind of trend we followed, and now what kind of trend we need to follow to achieve that kind of scaling and the performance from our computing system. So as we discussed, we have to think about material, device, processes, and architecture to cope up with that huge amount of data which we are getting from different sensors and different processing units and different applications. So on the basis of that, we can think about it, what kind of role VLSI can provide us to find out these kind of success in our VLSI designing and also application of the VLSI. So let's move on the application briefly, how we can think about the application. So from my perspective, as I mentioned in the starting of this presentation, that I think almost everywhere that VLSI is present. It can be from consumer market to automobile or any, like you can think about it. You can go to the space, but without VLSI you cannot, because you need a different kind of system. Even for example, if I gave an application, you can just test or test a sample from Mars, and you process that one. Later on, you need to test air velocity, for example. Then how can you achieve that one without any another program? Then you can reprogram that system, and that can be, for example, of FPGA. You can reprogram that FPGA in the sense that it can also sense, or it can also predict or analyze the different kind of inputs. So like that. So any anything which you can think about which has to be controlled by electronics, it would be VLSI. So any controlling unit. So from World War, as I connected, so from in World War, there were many inventions like automobile, aviation, consumer market also, but they need to be controlled. And to control them, there were electronics which has generated from that time also. That is why electronic was the major invention from the World War. Because of that, we were able to control all these other inventions. That is why everywhere you will find the VLSI present in the form of processing units or control units. So this is the another one, that professional development. You know that any kind of mobile, any kind of processing unit, laptop, iPad, cell phones, they have these chips inside there, and these chips have billions of transistors. You already have, and even microprocessing unit in the mobile has more power, in the sense of that it needs more dense processor to process all these kind of data which you are dealing with. And your single mobile has many different kind of sensors, like gyroscope, velocity sensor, temperature sensor. Many sensors are there. So it has to process each and every sensor data in that one. So that is why there's a many different application of the VLSI inside your cell phone. Now we can also think about, based on these applications, that what are the opportunities for the student or any person who is enthusiastic in the VLSI design field. There are many applications, as you can think about here. Then you can also think about the what is, but actually how can we build a new industry for that one. So as we go through this presentation, we can also think about the fabrication instrumentation. So what I was talking about, for example, patterning, for example, etching. So how can you efficiently etch those nanosheets? How can you achieve, how can you make the pattern for those nanosheets? If you can come up with a new instrument that can do that one, that is your business setup. It is not, I'm not just saying. Many people are working on metrology. They, for example, metrology, you have developed a metrology house. You have a setup. Then you can take a project from other design house, and for example, you can measure the thickness of your thin film. You can measure your devices like that. So from that metrology also you can make a setup. CAD tools, they are, everybody I think know that how important they are. So each and every device or MOSFET device, you have a model, and that model utilized by that system, and on top of that you build a circuit, you build a system, and that CAD tool is very necessary. So for the new devices, for example, from MOSFET to FinFET, you must have new model, and you must have new, I would say, platform or program, or the, I would say, GUI, so that you can build that circuit. How can you build a circuit with the previous MOSFET based CAD tool? It is not possible. You have to optimize that. So each level, from starting from fabrication, from CAD tool to designing or device structure or scaling, you have many opportunities here that you can make a setup, industrial setup, that you can continue further with that one, and you can take the projects and many things, and you can also achieve new technological advancement in there. So there are many opportunities, and people are already working, even in India, because many fabrication units, as we have seen, that only 3 fabrication foundries are there: Intel, Samsung, and IMEC. So it is very difficult to cope up with the new challenges. If you can come up with an industry which can allow us to fabricate those new technologies, processing units, with the cost effective way, then it is very good. And people are thinking in that way also, because India doesn't have that kind of fabrication possibilities. So we could have that one. So many different possibilities in terms of the business opportunities are there in the market itself. And research opportunity, I think if you are going for the business opportunity, you can also think about the research. Otherwise, basic field of the research are normally start from the device structure, also modeling. Device, I'm talking about the MOSFET device. Device modeling means the modeling of the parameters, how your device will behave. That is very, very important, because in case of FinFET, you must have the I would say idea and the exact model of that device, so that you can make a circuit and system. Because it is difficult, because planar MOSFET were different, very, very different from the FinFET and gate all around, and they offer different kind of capacitance. They offer different kind of layout effects. They also pose many fabrication problems. That is why your model must have all those parameters come from the fabrication, layout, and circuit design perspective. So that's why device modeling is very challenging at this time. So, and at circuit level, you have analog design, that is full custom design. You can make that one. It is very, very challenging also. But although it has very small part in a microprocessor, but it's very, very important in a microprocessor. So, and digital design also, digital circuit design, it is very important for whole system, because most of the part of your system is a digital circuit there. So these are the research opportunities. So with that application and opportunity in the mind, and how can you achieve that one, I would like to finish my presentation here, and I hope you all enjoyed that one. And I think everyone has taken something from my presentation, and I wish that it was successful. So thanks for joining me, and good afternoon again. Thank you.
Thank you so much, sir. On behalf of our institution and our audience, thank you so much for providing your valuable time and insightful knowledge. Sir, here are some questions that are asked by our audience. I will read them for you. Sir, there is a question. What are the different based algorithm used for 3D ICs floor planning?
Just a second. Can you repeat the question?
Sure, sir. What are the different best algorithm used for 3D IC floor planning?
See, I worked on algorithm like that was bio-inspired algorithm. That is normal genetic basic genetic algorithm that depends upon the mutation of each time, how it is going there. So that was the possibility in my sense. But otherwise, so what was happening there, on the basis of bio-inspired algorithms, I was able to develop a technique by which you can design a layout automatically. So for example, in FinFET, you can, for example, bit cell. I designed that bit cell for ARM research, and that was based on the Weinspart algorithm. And I was able to design that system. And the idea was that how can you fit that bit cell if I'm going to change the size of that bit cell. For example, 1 millimeter square to 2 millimeter square. Then how can you change that 1 millimeter, 2 millimeter square area to 1 millimeter square without doing anything manually? So with that algorithm, I was able to do that. Also, I was able to do that not with that uh, algorithm. Also, it was optimization. So what does mean? How can you optimize, for example, speed, power, and area? How can you optimize that these three parameters of that cell or any circuit with the help of algorithm? And I was able to do that one. So what does mean? This is one example of the algorithm that you can utilize to optimize the circuits. Similarly, there are many different algorithms, but exactly what kind of algorithm design houses are using, I do not know exactly, because they are using their own algorithm. So I do not know exactly what kind, but I used this kind of algorithm, and especially I used, I would say, the JavaScript for that, and with the model. So you can use Java or any programming technique to optimize or to design these kind of patterning. But I think for industrial, I do not have exact knowledge of what they are doing. Although I worked at IBM, you cannot access that one. But yeah, might be possible that you can find online somewhere that what kind of algorithm they are using.
Sir, here is another question. How VLSI is connected to radar system?
At this moment, again, as I don't work on radar system, but as we can think about, for example, as I was talking about the control, so you can think about this application, that how that system can be more efficient with the help of processing. For example, you are throwing a wave to the aeroplane and it's coming back. How quickly you can process that one, and that process of communication also can be just like mobile communication. It is not mobile communication, but communication also. How can you reduce this that communication delay, and how would you process that data at your system? So that processing data system would be a VLSI system. So that can be an application, and that could be application there already.
Sir, here is another question. Sir, how can we enhance the fabrication process?
So as I mentioned there also in the industrial perspective, that you have to find out, just like for example, from going from MOSFET to FinFET, you have to find out the technique. How can you, for example, deposit a layer efficiently, or I would say more easily, in the cost effective way, then you would be achieving that kind of application. Like for example, I was talking about the for example, diffusion. You have different technique for diffusion. For patterning, you have different technique for the patterning. For example, DI-BSD, it is a technique for patterning. And also like implantation, you have ion implantation technique. So there are different techniques based on the, I would say, the material as well as the technique of how you provide that to your fabrication. So in that sense, you can achieve that.
Sir, here is another question. Sir, any limitations of Moore law?
As I told, that Moore's law was introduced for 1 decade, starting in the starting 1 to 2 decades, and then again it revamped, and it is already, I would say, invalidated because of, as I told, it was difficult to continue with that. So around 22 nanometer or before that, it was already not in the market, but because of, as I told, it is a motivation to achieve that kind of scale. So because of that motivation, we were able to achieve that scale uh, parameters, like from 90 nanometer to 45 nanometer to 28 nanometer to 32 nanometer and 14. So these are around two transistor were increasing in the number. Okay, they were not exactly. Still, it is not valid. That Moore's law is not valid. There, it is called beyond Moore's law or more than Moore. It's not an exact Moore's law, but as I'm saying, it is a motivation. It's not just a law. So because of that, it is still valid, but in the another sense, that beyond CMOS. So we were talking about FinFET devices. So they are beyond CMOS, and Moore's law was previously stated like that. So yes, Moore's law is not valid in one sense, but it is valid in another sense, that we are going beyond the Moore's law, or more than Moore, it is called.
Thank you, sir. Due to limitation of time, we can't answer more questions. But if you have any more queries, you can contact us. Thank you, sir, for the wonderful session.
Thanks a lot again for everyone to be here, and I would say that it was lovely experience for me. Thank you.
Thank you, sir.
Bye bye.